Section 10.3 is parametric equations in calculus. In this section, we're going to look at finding the derivative of parametric equations. We're also going to look at finding the equation of a tangent line to a parametric equation, look at where parametric equations have horizontal tangents and vertical tangents, and then we're going to end with looking at arc length and surface area of revolution for parametric equations. Let's start with the derivative. We say that if we have a smooth curve C given by the parametric equations x equal f of t and y equal g of t, then the slope of that smooth curve C at a point xy is equal to dy dx is dy dt divided by dx dt. And this is going to be where dx dt doesn't equal 0. So the derivative of a parametric equation dy dx is equal to dy dt over dx dt. The second derivative of y with respect to x is found by the derivative with respect to t of dy dx over dx dt. Let's talk about why that is. Now the reason for that is this right here is really the derivative with respect to x of dy dx. But the problem is that dy dx, this guy right here, is a function of t. So really what we're doing is we're saying, well, I need to take the derivative with respect to t of dy dx. But what that is equal to is the derivative with respect to x of dy dx times the chain rule, which then tells us that we have to take the derivative of x with respect to t. Solving for this guy here, which again represents that second derivative, and I'm going to write the second derivative piece on the left over here. So this guy here would equal this, the derivative with respect to t of dy dx divided by dx dt. So that's why that second derivative is the derivative with respect to t of dy dx divided by dx dt. Let's practice finding dy dx in the first two examples. Example 1 gives us that x is equal to 6t squared and y is equal to 1 minus the cube root of t. If I need to find dy dx, I know that that's equal to dy dt divided by dx dt. So I need to find the derivative of y with respect to t and the derivative of x with respect to t. So let's begin by just finding the derivative of each one of these with respect to t. If I have x equals 6t squared, instead of writing dx dt, I'm going to write x prime. X prime here would be 12t. And the other one here, if I have y equals 1 minus, and instead of the cube root of t, I'm going to write it as t to the 1/3. Y prime is going to equal negative 1/3 t to the negative 2/3. Therefore, we know that dy dx is going to equal dy dt, this guy right here, this negative 1/3 t to the negative 2/3 divided by 12t. Cleaning this up, this is a negative exponent. Moving it to the bottom, I know that I would have 12t times t to the 2/3, and we'll combine that in a second. And then this guy's already in the denominator, so it also goes in that denominator. And all that's left in the numerator here is this negative 1. Therefore, dy dx is going to equal negative 1 over 3 times 12 is 36. And then t times t to the 2/3 is t to the 5/3. Let's look at number 2. Again, we need to find x prime. If x is equal to e to the t, x prime is also equal to e to the t. Y here is e to the negative t over 2, which we know that we could write as negative 1/2 t. Y prime would then be negative 1/2 e to the negative 1/2 t. Therefore, we know that dy dx is going to equal this negative 1/2 e to the negative 1/2 t divided by e to the t. Breaking this guy down, dy dx is equal to, well, notice that's already in the denominator. Go ahead and bring it down, and then we'd have e to the t times e to the 1/2 t. And again, combining those two like bases, we'd end up with negative 1 over 2e to the 3/2 t. Example 3 wants us to find dy dx, the second derivative of y with respect to x, the slope and the concavity at the given value of the parameter. Well, remember, slope is found by the first derivative, and concavity is found by the second derivative. And the given value of my parameter here is t equals 6. Let's start by finding that first and second derivative. Here x is the square root of t minus 5. We're going to write that as t minus 5 to the 1/2 to make it easier to take the derivative. What is the derivative? Well, x prime is going to equal 1/2 times t minus 5 raised to the negative 1/2 times the derivative of the inside, which is just 1. If I clean that up a little bit, that'll become 1 over 2 t minus 5 to the positive 1/2. Y here is equal to 4 minus t squared, therefore y prime is negative 2t. If we put all this together, dy dx is going to equal this negative 2t divided by 1 over 2 times t minus 5 to the 1/2. But the problem is we're dividing by a fraction, and we know that that's going to be the same as multiplying by the reciprocal. So if I take the reciprocal of this guy, that is 2 times t minus 5 to the 1/2. In the end, dy dx here is going to equal negative 2 times 2, or negative 4t times t minus 5 to the 1/2. Now I have to find the second derivative. Now remember, the second derivative had two pieces to it. It was that the second derivative of y with respect to x here is going to be the derivative with respect to t of dy dx divided by dx dt. Now I already have dx dt, that's over here, but I need to find the derivative of this guy here with respect to t. So we're going to do that first. The derivative with respect to t of dy dx is going to equal, well, this here is a product, so I have to use the product rule. So it's going to be the first term here, which is that negative 4t, times the derivative of the second. Well, I already know what the derivative of t minus 5 to the 1/2 is. I found that out right here, so I'm going to write that simplified form, and that is going to be 1 over 2 times t minus 5 to the 1/2. So the first times the derivative of the second, plus the second, which is that t minus 5 to the 1/2, times the derivative of the first, which is just negative 4. Cleaning this up, I have negative 4t in the numerator and 2 times t minus 5 to the 1/2 in the denominator, and that becomes just a negative 2t over t minus 5 to the 1/2. And then plus, well, plus a minus here is just going to be minus 4, and then t minus 5 to the 1/2. So now let's find that second derivative. So the second derivative of y with respect to x is going to equal what we just wrote down, and this guy right here, this negative 2t over t minus 5 to the 1/2 minus 4 times t minus 5 to the 1/2 divided by dx dt. Well, dx dt is this guy. But remember, if we're dividing by that, we're just multiplying by the reciprocal. So if we just multiply this guy by the reciprocal, we'd be multiplying by 2 and then t minus 5 to the 1/2, because that would be the reciprocal of that. If I distribute, I'd end up with negative 4t. The t minus 5 to the 1/2 will cancel. And then to here I'd have negative 8, and then t minus 5 to the 1/2 times t minus 5 to the 1/2 is just going to be a t minus 5. So again, we have to divide by dx dt, but dividing by the dx dt is the same thing we did over here. It's just multiplying by that reciprocal. And then we take this guy and we multiply it to this term. The denominator cancels, and that's just your negative 4t. And here, negative 4 times 2 is negative 8. And then t minus 5 to the 1/2 times the t minus 5 to the 1/2 is this t minus 5. If I clean up here, negative 4t minus 8t plus 40, I'd end up with negative 12t plus 40. So the second derivative of y with respect to x here is negative 12t plus 40. Now I need to find the slope and the concavity. So for the slope, I need to plug in the given value of t into this first derivative. So finding the slope right over here, we'd have dy dx evaluated at t equals 6, and that's going to be negative 4 times 6 times 6 minus 5 to the 1/2. Plugging in again a 6 for my t's. So that's going to be negative 24 times 1, or just negative 24. So the slope is negative 24. What about the concavity? Well, my concavity is going to be that second derivative evaluated at the given value of the parameter. So the second derivative here, evaluated at t equals 6, is going to be negative 12 times 6 plus 40, and that's just negative 36 plus 40, or 4. Let's do it again for example 4. I need to find dy dx, the second derivative of y with respect to x, and then find the slope and the concavity at the given parameter of theta, and in this case that's going to equal pi. So this is my x. If I take the derivative of x, I get that x prime is equal to 1 minus the cosine of theta. And this is my y. If I take the derivative of y, I end up with positive sine theta. Therefore, my dy dx is going to equal y prime over x prime. And for this one, there's nothing that I can clean up. Now I need to find the second derivative. In order to find the second derivative, I first need to find the derivative with respect to t of dy dx. Well, that is going to need the quotient rule. So let's do the quotient rule on this. It's the bottom times the derivative of the top. Well, the derivative of the sine is the cosine, minus the top, which is the sine, times the derivative of the bottom, which in this case is going to be sine of theta again, all over the denominator squared, which is that 1 minus the cosine of theta quantity squared. If I distribute here, I'd have cosine of theta, and then minus cosine squared theta, and then minus sine squared theta, all over 1 minus the cosine of theta squared. Notice that both of these guys are negative, so I can factor a negative from them. If I were to do that, I'd end up with cosine of theta, negative, and then that's cosine squared theta plus sine squared theta, again factoring out that negative. Well, if I do that, I have cosine squared theta plus sine squared theta, and I know that that's equal to 1. Therefore, this is the cosine of theta minus 1. Notice that looks a lot like the denominator, it's just a little different. If I were to factor out a negative from the numerator, I'd end up with a negative cosine of theta plus 1. And then if you look at that, that's the exact same thing that's in the denominator, because that denominator is a 1 minus the cosine of theta squared. So positive 1, negative cosine. Therefore, you can cancel one of those out, and then you know that the derivative with respect to t of dy dx is just going to equal negative 1 over 1 minus the cosine of theta. Now let's find that second derivative. So the second derivative of y with respect to x is what you just wrote down, this negative 1 over 1 minus the cosine of theta, divided by dx dt. So we're dividing it by 1 minus the cosine of theta. Well, dividing is the same thing as multiplying by the reciprocal. If we were to multiply that by the reciprocal of this guy here, that's going to be a 1 over 1 minus the cosine of theta. And that means that this second derivative of y with respect to x is negative 1 over 1 minus the cosine of theta quantity squared. So I have the first derivative and I have the second derivative. Now I need to find the slope and the concavity. So the slope is going to be where I evaluate the first derivative at the given value of the parameter. So we need to evaluate dy dx at theta equals pi, and that's going to equal the sine of pi over 1 minus the cosine of pi, and that's just going to be 0 over 1 minus a negative 1, which is 0 over 2, or 0. So my slope is equal to 0 when theta is equal to pi. What about the concavity? Well, my concavity is evaluating this second derivative at theta equals pi, which is going to be negative 1 over 1 minus the cosine of pi, quantity squared, which is going to be negative 1 over 2 squared, or negative 1/4. Therefore, the concavity at theta equals pi is negative 1/4.